So in this video, we're going to recap sampling distributions. So let's start off with pretending we have some population that we're interested in. I'm going to pretend at the moment that the population is the people of Australia. And let's pretend that we're interested in the heights of the people of Australia. So we would assume that the heights of our people are going to be normally distributed. So we have two aspects that define a normal distribution. One is the mean and one is the standard deviation. So of our population, there's going to be a fixed value for the mean or the average height of all the people. And there's also going to be a fixed value for the standard deviation, so how variable people's heights are across the population. Now, obviously, it's going to be very, very difficult for us to go out and measure the height of every single person in Australia's population. So rather than doing that, what we would probably do is pick out a sample of people to use as like a representative sample. So let's pretend that's this green dot here. Okay, this is a sample of people. Say we pick out 50 people and we measure their heights. So what we're going to be interested in is how this sample of people's heights is distributed. Okay, and that's known as the sampling distribution. Okay, the distribution of the sample. And what we're going to find is that if our population is normally distributed, which we've just assumed, then our sample distribution is also going to be normal. And remember again, a normal distribution is defined by just those two attributes of mean and standard deviation. So we're going to use slightly different symbols here to represent the mean and standard deviation of our sample. So the first one, mean, we're going to use this. So it's mu with a subscript of x bar. And what this is measuring is the mean of the sample mean. So every time that we repeated this experiment, so say we pick out 50 people each time, it's going to be a different combination of 50 people each time from the population. There's going to be a mean value that we get for that sample. And this here is measuring the mean of that mean. Okay, so every time you repeat the experiment, measuring what the mean value is for the heights of those people in the sample, and then averaging again what you would expect the mean of the mean to be. Okay, so it's a bit of a mouthful, that one. Alright, so the other aspect we said was that we wanted the standard deviation of our sample mean, and that's what this symbol here is. So sigma for standard deviation, subscript x bar for the mean. So this here is the standard deviation of the sample mean. So how does it vary? Okay, every time you repeat the experiment, potentially you're going to get a different value for the sample mean, and this is measuring the variation in it. This also has another name, so also known as, and that's the standard error. So both of these terms are the same thing. Alright, so for this example here, let's go ahead and draw our normal distribution curves. So let's start with the one for the population. So for the population, in our example, we were measuring people's heights. So that would be the variable x that we plot on the horizontal axis. So if it's normally distributed, we know that it's going to have a mean of mu. So whatever number of centimeters the average height of the population actually is. And it's going to have some standard deviation, which I'll pop over here, sigma. So now when we look at the sample, rather than the data for the population, it's going to be as well a normal distribution, we've said. So same kind of shape. This time though, what goes on the x-axis or the horizontal axis here is going to be x bar, okay, and that is the sample mean. Okay, so let me just mark that in. And we've said that the sample mean has a mean, so the mean of the mean, of mu x bar. Okay. The other thing we needed to define this distribution was the standard deviation. So that's the equivalent standard deviation for when we look at this distribution of the sample mean, rather than of just the directly observed values. So if we want to relate them together, alright, looking at the population and its sample, what we can say is that whatever the mean is for the population, we would expect to have the same mean of the mean over here. So mu x bar should be directly equal to whatever we had over here for mu. Alright, it's a little bit different though for the standard deviation. Because you're taking the standard deviation of the sample mean, what you would expect is that you get a smaller variation overall. So I'm not going to go through all the derivation of that or anything, but I'm going to provide you with the equation, and that is this one here. So it's equal to the standard deviation of the population, alright, divided by the square root of n, where n is the number in the sample. So if we took 50 people and measured their heights and looked at the sample mean, then this in here would be 50. So hopefully you can see that as the number in your sample gets higher and higher and higher, alright, in other words, making this bottom line here bigger and bigger and bigger, what's going to happen is that the standard deviation of your mean is going to get smaller and smaller from the inverse relation there. So that's pretty much it in terms of the equations that are required for the sampling distributions. The only other thing to mention is what happens if your population wasn't normally distributed. And of course we made that assumption right back at the beginning. So if your population is normal, we said that x bar is normal, which is the example we've just done here. However, if your population is not normal, x bar becomes approximately normal as n increases. Okay, so in other words, if your sample, so n, the number of things you're drawing out of your population, is a really big number, then you can assume that the mean of your mean is going to be approximately normally distributed as well. So as a rule of thumb, people tend to say that if n is greater than 30, alright, then you can make this assumption that x bar is indeed a normal distribution. And then all these other rules, still apply. Alright, so that's all there is for this video, and I'll see you in the examples.